it's time for Lesson 8, Tree Diagrams with and Without Replacement and Conditional Probability. Again, let's start with a warm-up just to get started. Here we go. So Robin plays a game in which she randomly chooses one of these 5 cards. She plays the game 60 times, so that's important, 60 times, replacing the card after each game. That's also important. How many times would she expect to win $4? So this is a bit of an expectation problem. So to begin with, what is the probability that she would win $4? So you can see there's 3 cards where she wins $4 out of 5. So it'll be 3/5. But how many times? So there's a 3 in 5 chance, and she does it 60 times. So it's 3/5 times by the number of times you repeat the experiment, which would give you, if you were to do it by hand, 180 divided by 5, and then try to think what is 180 divided by 5. It would give you 36 times. So we expect 36 times that she would win $4, because 36 is basically 3/5 of 60. Next question, what is the financial expectation of the game? So we might want to start to answer that one down here because we need a bit more working out space. So by that we're kind of trying to work out, like, in just one particular game, not taking into account that you play it 60 times, but just for one game, what is the financial expectation for one game, because they say the game. So we already worked out that there's a 3 in 5 chance of winning $4. So 3/5 times $4, you don't need the dollar sign to be honest. So if you work out what's 3/5 of $4, you'll get $2.40. So that's a $2.40 gain. Okay, the next one is win nothing. So there's a 1 in 5 chance that you're going to win nothing. So 1/5 times $0, of course, gives you $0. And the last one is lose $8. So there's a 1 in 5 chance that you're going to lose $8. So what's 1/5 of $8? Basically, it's like 8 divided by 5. Gives you $1.60, but that's not a gain, that's a loss. As opposed to the wins are the gains and the losers are the losses. So what is the financial expectation overall? So let's do that over here maybe. So financial expectation will equal, it's a $2.40 gain plus a $0 gain and a $1.60 loss, so you're going to have to subtract that. So overall, per game, we expect an 80-cent gain. So actually, you might want to put a dollar sign there, or write 80 cents. So I'll put $0.80. You could also say an 80-cent gain is what's expected on average for every game. And part III says another card is added to the game. So for example, we've got another one here. And that card is win nothing, $0. So it's another win nothing, $0. You don't have to draw the card if you don't want, but sometimes it can help. Robin claims that the financial expectation will not change, i.e. it will stay 0.80. Do you agree and justify with suitable calculations? So we've got to do what you did up here again. Hopefully you've got some space to do that. So we'll do that again. Oops, sorry, back to here. Oops, sorry again. Okay, so again, we've got 3 win cards, but this time they're out of 6. 3 win $4 cards, but it's 3 out of 6 this time. So 3/6 multiplied by $4. What will that give us? That'll give us $2. Basically half of $2, half of $4. Then how many $0 cards do we have? Notice this one we have 2 out of 6. So 2/6 times 4. Let's see, we'll give you, oh sorry, not 4. 2/6 times 0, because that's win nothing. Of course we'll give you $0. And this, by the way, was a gain, so we probably want to write in gain. And let's see, how many lose $8 cards do we have? We've just got 1 lose card, and it's out of 6 though this time. So 1/6 times $8. So this is going to be a loss this time of $1.33. So now let's work out the financial expectation and see if it stays the same. So financial expectation will equal $2 gain plus a $0 gain minus, and then you've got a $1.33 loss. So what do we have this time? We have a 0.67 gain. So overall, it said, what we had to say was, do you agree? And so you could put don't agree. If you've got space, you can also point out that the financial expectation is not the same. It's not, this time it's 0.67 gain per game, and this is a $0.80 gain per game, so it's changed, so it's not the same. And the last question asks us, on the table, indicate with a tick or a cross whether the numbers in the left-hand column belong to Q, the rational numbers, Q plus, which means positive rational. You might not have seen that before, so just put that down. Positive rational, meaning not including 0. Z, which is integers, which of course does include 0. Z plus, which is positive integers, which does not include 0. Or natural numbers. And we've checked with our textbook, our course assumes natural numbers includes 0. So our natural numbers include 0. So that's important because you've got the number 0 in this particular question. So let's see. Rational numbers, first of all, Q. So are there any irrational numbers? Irrational numbers are ones where you can't express them as a fraction with an integer numerator and denominator. Or another way of explaining them is they're numbers, if you plug them into a calculator, you get an infinite amount of non-repeating decimals. So are there any like this on there? And no, there's not. So you can give them all a tick. So they're all rational. Let's see, what's the next one? Q plus. So these ones have to be positive rational. So of course you tick the positives and you cross the negatives. And notice Q plus means it's got to be positive. So 0 is neither positive nor negative, so we just leave that off. And that's a negative, so no. So only 2 ticks in that particular column. Z's are integers, so just whole numbers can be positive or negative. So whole number, not a whole number, because Z's do include the zeros, and not a whole number. So that gets across down there. Next one is Z plus, so positive integers, so it doesn't include 0 this time. So positive integers has to be a whole number too. So not positive, not a whole number, so don't include that one. Not a positive integer, because it's neither positive nor negative, and not a positive integer. And last but not least, we're on natural numbers, and remember our course says natural numbers do include 0. So natural numbers, let's say yes for that one, no for that one, because it's negative, no for that one because it's not a whole number, yes for this one because the CIE course assumes that 0 is a natural number, but depends on the course, again depends on the textbook. So our textbook, from the answers that we've seen, assumes that 0 is a natural number. And not negative, a half, because it's neither a whole number and it's also not positive. So let's move on to the next page. So first page of this lesson. So tree diagrams with and without replacement and conditional probability. So the following is important to remember from last lesson. So remember this, you calculate the probability of A and B, the intersection of A and B, by summing the probabilities together. So basically I've copied and pasted this from last lesson, so hopefully you remember that it's multiplying, by multiplying the probabilities together. So for example, probability A and B, so using the Venn diagram, that's the intersection part here. So probability of A and B equals the intersect, probability of A intersect B, which equals a probability of A multiplied by the probability of B. So when you see probability of A and B, they want you to multiply the probabilities together. Similarly, you calculate the probability of A or B, which is the union of A and B. So if you see or, it means union. And you calculate them by doing something to the probabilities together. And hopefully you remember it's by adding the probabilities together. So remember, union is probability of A or B, which means all of it, all of the circly bits coloured in. So let's shade that in just to help us remember our shading. So it equals a probability of A union B, which equals a probability of A plus the probability of B in that case. That's actually, to be honest, more so. Like, notice in this particular example, I've just noticed, this would be a better example if the Venn diagram kind of looked like this. So you might want to actually, what I would suggest doing is cross out this diagram and draw another diagram instead. So this happens to be when they're separate like that. So it's more like probability of A plus a probability of B. And you'll notice that when they're overlapping, from here you would actually have to subtract the intersect, but don't write this down now because this is mentioned in the following lesson, lesson 9 I think, or it's either this one, I'm not sure if it's lesson 8 or lesson 9. So just for the diagram for now, leave this one off and just leave them as mutually exclusive or disjoint sets, and then in that case this particular thing still does work. We don't need to subtract off the intersect. In this case you can see if you did A plus B, the intersect got shaded twice, which is why you have to, the union would be subtract the intersect because it got added in twice. So we'll just for now leave that crossed out. Okay, so moving on from there. So watch the first video on Firefly now for this lesson that's coming up on the next page in a bit, and complete the notes and examples on this page as you go. So these notes are all coming from the first video that you'll see on Firefly to do with probability trees for lesson 8. So I would pause this video now and I would then go and watch the other video on Firefly. So you might want to do that and then come back and we'll pick up where we left off on the next page. Okay, so assuming you've done that, let's skip ahead. So this part of course comes from the video, the first video that I was just talking about before. And now what we can do is we can do the summary together if you like. You might have already done the summary, but we can always do it again just to check that you've got the right answers. So from the tree diagram video, the first one on Firefly, you write the probabilities on the something of the tree diagram. So hopefully you thought you write the probabilities on the branches of the tree diagram. Next one. Vertically, the probabilities on each set of these something must add up to something. So each set of these branches from the first question. And so, for example, if you've got red and yellow, what must these two probabilities add up to? They must add up to 1. So, for example, you might have 2/5 on this one, so you've got to have 3/5 on the one below. So when the problem is with replacement, this means that the events are something. So hopefully you're guessing that it means independent. When the problem is without replacement, this means that the events are therefore dependent. Now, when the problem is written with replacement, the probabilities do something change as you go across the tree diagram. So you might have seen from the video in his first example, the probabilities do not change as you go across the tree diagram. So he might have had red, yellow, for example, red, yellow, and so on. So the probability, if it was 2/5 here, it remains 2/5 here for red. And if it was 3/5 here for yellow, it remains 3/5 here for yellow. When the problem is without replacement, the something of these fractions, these little fractions here, representing the probabilities, something by 1 each time as you go across the tree diagram. So it's the denominators. The denominators of these fractions representing probabilities decrease. So I'm just going to have to probably pause. Yep, I have to pause again and fix this up. Okay, here we are back again. So fix it up now so it's writing again. So the denominators of these fractions representing probabilities decrease by 1 each time as you go across the diagram. So here's an example. You've got red, yellow, that kind of thing. So if it was 2/5 for red on this one, as you go to the next red, there'll be only 4 left in the bag and only 1 red left in the bag. So here's an example that we can start to do our own tree diagrams. So Nina and Dika both play netball. The probability that Nina will score a goal on her first attempt is 0.75. The probability that Dika will score a goal on her first attempt is 0.82. So calculate the probability that Nina and Dika will both score a goal on their first attempts. So it doesn't tell us to do a tree diagram, but I'm going to do this one with tree diagrams. So the first event would be Nina's shot, and the second would be Dika's shot. So first event is Nina, second event is Dika, just because they happen to go in that order in the question. So the two options are that she gets the goal, and the other one is that she doesn't get the goal. So you can call it goal and non-goal, if you like, and you can put the probabilities on the diagram too. So they said 0.75 chance that Nina gets her first shot of goal, 0.75. So what must be the not goal for Nina? So these two must add up to 1. So this must be 0.25. Now let's do Dika's. So Dika's got the option of goal and not goal. So we've got to write goal and not goal coming off both of Nina's branches. So Dika's probability of goal on the first attempt is 0.82. 0.82, and these are independent events because the probability of Dika getting a goal isn't affected by whether or not Nina got a goal. So it's the same probabilities as you go across. So not goal, because these two, goal and not goal for Dika, have to add up to 1. Sorry, not goal must be 0.18, because 0.82 and 0.18 adds up to 1. Then you've got 0.82 and 0.18 again. So what's the probability of both of them scoring a goal? So notice that's following this branch here, so following goal and goal. So probability, we want to know the probability of a goal and another goal. So to work them out, we just multiply these two probabilities. You multiply as you go across the diagram. So 0.75 multiplied by 0.82, and if you bung that into a calculator, you'll get 0.615. If it happens to give it to you as a fraction, it should be 128 over 200. So you can write either decimal or fraction answer. I'll just write them both in for this particular one for you. What's the probability that neither Nina or Dika will score a goal on their first attempts? So we want to know what's the probability of not goal and not goal. So probability of not goal for Nina and not goal for Dika. So we're going from here to here, so we need to multiply those two probabilities. 0.25 multiplied by 0.18 should give us 0.045 or 9 over 200 as a simplified fraction. So as I said, you notice that we're multiplying as we go across the diagrams. That's important. So now let's move on to the next page. So this is talking about with replacement and without replacement, this section. So let's look at when we're talking about without replacement. So without replacement is when you pick an item from a bag, but you do not put it back. This means that when you pick your second item, there is one less to choose from. Like that's why the denominators are going down by 1. So a drawer contains 4 brown, 1 yellow, and 5 pink socks. Amy picks 2 socks from the drawer without putting them back. Draw a tree diagram to illustrate the scenario. So it's kind of been partially done for you here. So let's put in the outcomes first. So we've got brown, yellow, what was the other colour? Brown, yellow, and pink. So BYP is fine. And then coming off here, we've still got brown, yellow, and pink. Brown, yellow, pink. Brown, yellow, pink. Next step is to put the probabilities on the tree diagram. So let's see, what do we have? How many do we have in total? 4 plus 1 plus 5, total equals 10. So Amy picks 2 socks from the drawer, and so on. So 4 brown would mean 4 out of 10. I know in the first video he was simplifying the probabilities on the tree diagram, but to be honest, so long as your final answer is simplified, that's the main thing. So if you're not sure, you could always do this. 4/10 of the 2 equals 2/5. We've got 1 yellow and we've got 5 pink socks. So again, if you want to, you can do this. That simplifies to a half. So again, is this with or without replacement? This one is without replacement. So on the second set of branches, the denominator, if we've picked one sock out already and we're not replacing it before we pick out the next one, then our denominator should now be 9. So if I've taken a brown here, there's only 3 brown left out of a total of 9 socks. If you want, you can simplify it. Yellow, there's still only 1 yellow sock, but it's out of 9 this time. And pink, there's still only 5 pink socks, but again, that's just out of 9. On the second branch, though, we had a yellow first. So that means we've still got 4 brown socks, but it's out of 9 in total. So because there's only 1 yellow sock, there's a 0 in 9 chance of it being yellow. You can also omit, so sometimes on your tree diagrams you might either just write 0 out of 9 for yellow, or you can omit this branch entirely. Entirely, meaning that you would just have brown and pink instead. But I'll just leave it there with 0 over 9 for now. There's still 5 pink out of 9 socks in total. And again here, still just 4 out of 9. Because in this case you picked a pink, so you've still got 1 yellow out of 9 socks. But because you chose a pink, that's why I like to have these written here, because it's kind of helpful. So because you chose a pink, there's only going to be a 4 in 9 chance that you chose the second pink. So if you're asked how many outcomes you have, you would say, like, even though it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, in total there's really only, I would say, 8 outcomes, because the one in the middle you don't actually count, because it's a 0 in 9 probability for that one. So only 8 possible outcomes. You might just want to add it as an extra note. And now let's go into the next one, which is with replacement. So it's the same situation, 4 brown, 1 yellow, 5 pink, but it's with replacement this time. So total equals 10 still. With replacement, to be honest, it's a lot easier because the probabilities don't change. So I don't know why that's happening. So let's go BYP, brown, yellow, pink, brown, yellow, pink, brown, yellow, pink, and brown, yellow, pink. So our probability on this one is 4/10. If you want, equals 2/5. Here's 1/10, and this one is 5/10. And if you want, you can write equals a half. So I'm just going to put the unsimplified probabilities on the next one. So because you took this brown one out and you replaced it, you've still got the same amount of brown left, and there's still 10 socks in total left. So 4 out of 10, 1 out of 10, 5 out of 10. Same thing if you took a yellow, but then you replaced it, then you're still going to have 10 socks and the same amount of each colour to begin as you had to begin with. So same probabilities, 4/10, 1/10, 5/10. Same for this, 4/10, 1/10, 5/10. So how many outcomes do we have this time? We have 9 possible outcomes. So if you're not wondering what I'm meaning by outcomes, I mean getting a brown followed by a brown and a yellow and a pink, a yellow and a brown, a yellow and a yellow, a yellow and a pink, pink and a brown, pink and a yellow, pink and a pink. So that's what I mean by the outcomes. So how many outcomes do we have this time? We have 9 possible outcomes. If ever you're asked what are the outcomes. So next one. So what we've got down here is a new example. So the probability P here that Nanook gets up before 7 AM is 0.95. See, that's already on the diagram anyway. If Nanook gets up before 7, the probability T here that he arrives to school on time is 0.98. Again, that's been added already. If Nanook gets up later than 7, so this one, not P, the probability that he arrives to school on time, this one, is 0.55. And again, that's been done. So sometimes things that are written in the question are already on the tree diagram, but you need to read them just in case, because sometimes they might, like for example, maybe this one's not on there. The above information is represented in the following tree diagram. You can see question A is just to complete the tree diagram. So here they're just testing that. You realise that the sets of branches have to vertically add up to 1. So if this one is 0.95, then this one has to be 0.05, because these two add up to 1. If this one is 0.98, this one has to be 0.02. And if this one is 0.55, this one has to be 0.45. So the tree diagram has been done. B, calculate the probability that Nanook gets up before 7 and is on time for school. So before 7 means P, so this branch here, and is on time for school means this branch here. So we want to know what is PT, probability on time, gets up before 7 and is on time, because P is the probability gets up before 7. So I'm going to do that in the space down here though. So we're going to multiply these probabilities. So we want to know the probability of probability of P to begin with, probability of P and T equals 0.95 multiplied by 0.98. So throw that into your calculator and you get 0.931 or 931 over 1,000 if you're to write it as a fraction. Again, it's up to you if you want to write it as a decimal or a fraction. Calculate the probability that Nanook does not arrive on time to school at all. So there's two outcomes. There's two ways he can not arrive on time to school. It's this one followed by that one, plus also this one followed by that one. Because see, there's two cases of not arriving on time to school. So we've got to multiply this by this and then add it to the product of that times that. So let's write that out. So it's like saying in symbols the probability of P and not T plus, because it's like an or question, or this outcome, the probability of not P and not T. So there are two branches. So from the tree diagram, the first set of branches is that one by that one. So 0.95 times 0.02. So 0.95 times 0.02. That's the first one. And notice in the first video he puts brackets around it like this, but I tend not to, I just underline. Plus probability of not P is 0.05 and not T 0.45. So that's 0.05 multiplied by 0.45. And you can work those two things out separately if you want, or you can just throw it all in the calculator at once, it's up to you. So if you were to work it out bit by bit, 0.19 is the first one, plus 0.0225 is the second one. And if you've got space, write it down here, or if not to the side. You get 0.0415, or 85 over 2,000. Next example. So, box A contains 3 pink plus 2 yellow roses. So how many is that in total? Total equals 5. Box B contains 1 pink and 4 yellow roses. So that's again total 5. So 2 separate boxes. A box is randomly selected by tossing a coin. So, and 1 rose is removed from it. Determine the probability that it's yellow. So try to think what event comes first in time. Is it choosing the rose, or is it choosing the box? So first of all, they seem to be choosing the box by tossing a coin. So what are the 2 outcomes of tossing the coin? So tossing a coin. This has happened again, so I have to pause it. Here we are back again with it all fixed up. So tossing a coin is the first event. toss a coin, and picking a flower is the second event. So let's see, so coin tossing, the outcomes for the coin tossing are just box A or box B. You can write box A and box B if you prefer. And the probabilities, when you toss a coin, you can either get a head or a tail, and it's a 50-50 chance, so 1 in 2, 1 in 2 chance. So a 1 in 2 chance of getting box A, 1 in 2 chance of getting box B. The second outcome is picking the flower. So we've got either pink or yellow in box A. Box B also has just pink and yellow. And the probabilities for that. So the first one, we've got 3 pink out of 5. So 3 out of 5 for that one. So yellow is 2 out of 5. Second box, box B, we've only got 1 pink out of 5 and 4 yellow out of 5. So we've got to determine the probability that it's yellow. So as you can see, there's 2 outcomes. You can get box B in yellow, or you can get box A in yellow. So we've got to work out those 2 probabilities and then just add them together. So I can do it kind of around the tree diagram. Let's do it here. So A and then Y yellow is a half multiplied by 2/5, which gives you 2/10. And it's not the final answer, so we don't need to simplify yet. Now let's do box B and yellow would give you 1/2 multiplied by 4/5, because it's a box B and yellow, which would give you 4/10. And the clue is you just add them together. So the thing is with tree diagrams, you multiply going across and you add going down like this. So 2/10 plus 4/10, what does that equal? 2/10 plus 4/10 equals 6/10, which simplifies to 3/5, or you can say 0.6 as well. So there's a 3 in 5 chance that the rows will be yellow. Next one, Carl is not having much luck lately. His car will only start 80% of the time. Oops. And his motorbike will only start 60% of the time. So draw a tree diagram to illustrate this situation. So the first event could be his car. Let's assume that the first event is he tries to see if his car is working. And the second event is he tries to see if his bike is working. So you could have done bike and car, it doesn't matter. I'm doing car, then bike. So the options are it could start or it could not start. Try to think what the probabilities are. His car will only start 80% of the time, so as a decimal that's 0.8. Put 0.80 if it helps. So probability of not start, because these 2 branches must vertically add up to 20. Sorry, add up to 1. So 0.8 plus 0.2 adds up to 1. Bike as well has the same outcomes, start and not start. Start and not start. Let's put the probabilities on there. So probability it will start is 0.60, so that must be 0.40 chance that it doesn't start. So that one just wanted us to do the tree diagram to begin with. Then B, use this tree diagram to determine the probability that both the car and the motorbike will start. So that's like saying probability of a start and a start. So as you can see, that's going to be this one multiplied by that one. So that's going to be 0.80 multiplied by 0.60. And what does that give you? That gives you 0.48, or 12 over 25. So that's exactly 0.48, an exact answer. Carl has no choice but to use his car. So no choice but to use his car means that the car is starting, but the bike is not starting. So that means car is starting, but the bike is not starting. That's the outcome that would lead to him having to use the car. So probability of a start and a not start. If you want, you might want to remind yourself, this is the car and this one is the bike. So you're going to multiply those red probabilities together. So 0.80 car starting multiplied by bike not starting, 0.40, will give you 0.32 or 8/25. And I think this is the last page in this particular lesson. So conditional probability. So it's not really specifically stated in the syllabus that you need to do conditional probability for this course, but there is a question or two in the textbook that includes the words given that. And as it says here, if a question contains the words given that, the question is highly likely to be about conditional probability. That's why it's important to include a page and an example of conditional probability. For example, find the probability that New Zealand will win the rugby given that it rained this morning. Sometimes I notice the words given that are in there, which means it's conditional probability. Sometimes you can work it out logically, like just according to what makes sense in the real world. However, there is also a formula that you can use. So this thing here, probability A, line B, means the probability that A occurs given that B occurs. So the situation that is given that occurs is the second letter. So find the probability that A occurs given that B has already occurred. And notice the way you calculate it by working out the intersect. So it's a probability of A and B. And you divide it by the probability of B down here. Probability of B. So probably will make more sense if we use an example and apply that. So in a class of 40, so we know total equals 40. We know 34 like bananas, 22 like pineapples, and 2 dislike both fruits. If a student is randomly selected, find the probability that the student likes both fruits. So different ways you can do this, but just I'm going to do a flashback and make us do a Venn diagram. So they're saying they want us to see what is the probability that they like both fruits. So basically they want us to work out the intersect. So we've got bananas here and pineapples there. They want us to work out this thing here. Oops. Bananas, pineapples. And don't forget to label the universal set. So let's see. So we know that there's 2 that dislike both fruits. So we know we've got a 2 out here. So the union, basically this thing, union must equal 40 minus 2. So there must be 38 in total in that union. But if you add up total bananas and total pineapples, you'll get 34 plus 22 equals 56. So to find the intersect, this little part here, so to find the intersect, we go what the 2 circles added together are, minus what they're supposed to be to get what the overlap is. So we know that the intersect must be 56 minus 38, which when you work that out, you should get 18. So what you do is you work out what the union should end up being, 38, work out what the 2 circles added together are, and 56, and the difference there gives you what the overlap, the intersect is. So that's hopefully going to help us to answer this question. So find the probability that the student likes both fruits. So that's just the intersect. Also, it might be helpful to work out the rest as well. Bananas, there's a total of 34 bananas. 34 minus 18, we get 16 here. And total pineapples is 22. 22 minus 18 gives us 4 here. And just check, 16 plus 4 plus 18, yes, that gives you 38. And you've got the 2 on the outside. So now let's work out those answers. So A, probability that they like both fruits. As you know, it's just 18 over 40 in total. That simplifies to 9 over 20, because we can divide the top and bottom by 2. B, likes at least one fruit, means that, and that. So they can like one fruit or 2 fruits. So 16 plus 18 plus 4, we know already that that's meant to add up to 38, but I'm going to show it anyway, equals 38 over 40, which equals 19 over 20. That's A and B. Now let's do C and D. C and D are conditional probability. That's why I said make sure to use the formula. So probability likes bananas, given that they like pineapples. So using this formula up here, I'm going to use it in this style. So probability likes bananas, given that they like pineapples. So bananas given that they like pineapples. So remember, it's the intersect of the two over the probability of the given that situation, which in our case is pineapples. So equals the probability of the intersect, bananas intersect pineapples, over the probability of the pineapples. And you just work them out. Probability of bananas intersect pineapples is 18 over 40. And instead of doing it as a fraction, I'll just write the divide sign. It's a bit easy to write on here. Probability of pineapples, there's 22 pineapples in total. So divide by, I wrote 40 here, 14 instead of 40, not sure why. So 22 out of 40. Remember with your fractions, remember you keep, change, flip. Keep the first fraction, change the divide to a multiply, and flip the second fraction. And we can cancel down 40 and 40. So the answer is 18 over 22, which simplifies to 9 over 11. So we're almost there. We've just got to do D in the same way. Dislikes pineapples, so P dash, given that they like bananas. So probability, dislikes pineapples, P dash, given that they like bananas. So again, that's going to be the intersect of P dash, so P dash intersect B, over probability of the given that situation, over probability of B. And then looking at your Venn diagram, let's see how many are in the intersect of not pineapple and banana. So not pineapple means everything outside of the pineapple circle that intersects with bananas. So as you can see, there's only 16. So that's 16 out of 40. Again, I'll just say divide. Bananas, we know already from the question that there's 34 bananas in total. 34 out of 40. If you're running out of space, just write it off to the side. Equals, keep, change, flip, 16 over 40 times 40 over 34. Cancels down the 40. Equals 16 over 34. Cancels down to 8 over 17. And that's the end of the lesson.